We imagine the universe as a vast space dotted with a multitude of galaxies, which make up billions of stars, different in color and size. Trillions of different exoplanets orbit around these stars. We also know that there are enormous distances between star systems, between stars and exoplanets. What is between them? Is there an empty space or vacuum? There are small solid particles that are a fraction of a micron in size. Cosmic dust. It is often divided into interplanetary and interstellar, although obviously interstellar dust is not forbidden to enter interplanetary space either. Interplanetary dust, at least in the comparative vicinity of the Earth, is a fairly well-studied matter. Filling the entire space of the solar system and concentrated in the plane of its equator, it was produced mostly as a result of random collisions of asteroids and the destruction of comets that approached the Sun. The composition of the dust is essentially the same as that of meteorites falling to Earth. Due to such dust, it is possible to admire a pale cone of light over the horizon in good weather in the west, just after sunset, or in the east before sunrise. This is the so-called zodiacal sunlight scattered by small cosmic dust particles. However, interstellar dust is a whole other story. Its distinctive feature is the presence of a solid core and a shell. The core seems to consist mainly of carbon, silicon, and metals. The shell consists mainly of gaseous elements frozen on the surface of the core, namely hydrogen and oxygen crystallized in the deep freezing conditions of interstellar space, and this is about 10 Kelvin. However, there are also more complex molecular impurities. These are ammonia, methane, and even multi-atomic organic molecules that stick to the dust or form on its surface during its wanderings. Certainly, some of these substances fly away from the surface, for example, under the action of ultraviolet light, but this process is reversible. Some fly away, others freeze or synthesize. It must be said that the very notion of the cosmic vacuum is something completely empty has long remained only a poetic metaphor. In fact, the entire space of the universe, both between stars and between galaxies, is filled with matter, fluxes of elementary particles, radiation, and magnetic, electric, and gravitational fields. Roughly speaking, the only things that can be touched are gas, dust, and plasma. Gas is the most abundant in space, almost 99%, and then there's dust, which is almost 100 times less massive than gas. This matter is distributed in interstellar space very unevenly. Most of the interstellar gas and dust form a gas-dust layer near the symmetry plane of the galaxy disk. Its thickness in the Milky Way is several hundred light-years. Most of the gas and dust in its spiral arms and nucleus is concentrated mainly in giant molecular clouds ranging in size from 5 to 50 parsecs, 16 to 160 light-years, and weighing tens of thousands or even millions of solar masses. But even within these clouds, the matter is also distributed inhomogeneously. In the main volume of the cloud, the so-called coat, mostly made of molecular hydrogen, the density of particles is about 100 pieces per 1 cubic centimeter. In densifications inside the cloud it reaches tens of thousands of particles per 1 cubic centimeter, and in the cores of these densifications, millions of particles per 1 cubic centimeter. Stars, planets, and, ultimately, we ourselves owe our existence to this unevenness in the distribution of matter in the universe. Indeed, stars are born precisely in molecular clouds, which are dense and relatively cold. Interestingly, the higher the density of the cloud, the more diverse is its composition. In addition, according to the spectra, there are substances in interstellar space, the existence of which in Earth conditions is simply impossible. These are ions and radicals. Their chemical activity is so high that they immediately react on Earth, while in the rarefied cold space, they live long and quite freely. Finally, near the hot stars, gas exists in the form of ions. Powerful ultraviolet radiation heats and ionizes the gas, and it begins to glow. This is why regions with high concentrations of hot gas, with temperatures of about 10,000 K, look like luminous clouds. These are called luminous gas nebulae. Any nebula, in greater or lesser amounts, contains interstellar dust. Although nebulae are conventionally divided into dust and gas nebulae, they both contain dust. In either case, it is the dust that seems to help stars form in the interior of nebulae. Nebulae may be the most beautiful of all cosmic objects. However, dark nebulae appear simply as black blobs in the sky in the visible range. They are best observed against the background of the Milky Way. Whereas in other ranges of electromagnetic waves, such as infrared, they can be seen very well, and the pictures are very unusual. An interstellar nebula looks bright in two cases: either it is so hot that its gas itself glows, such nebulae are called emission nebulae. The other case is that the nebula itself is cold, but its dust scatters light from a nearby bright star. They are called reflection nebulae. Dark nebulae are also interstellar clusters of gas and dust. But unlike light gas nebulae, which are sometimes visible even with high-power binoculars or telescopes, such as the Orion Nebula, dark nebulae don't emit light but absorb it. When starlight passes through such nebulae, the dust can completely absorb it, converting it into infrared radiation invisible to the eye. This is why such nebulae look like starless gaps in the sky. Perhaps the most spectacular of these is the Horsehead Nebula. However, the dust particles may not completely absorb the light of stars, but only partially and selectively disperse it. The fact is that the size of interstellar dust particles is close to the wavelength of blue light, so it is more scattered and absorbed, while the red part of starlight reaches us better. So what is the role of dust in the formation of stars? And where, in fact, does it come from? In the total mass of cosmic matter, dust proper, for example, atoms of carbon, silicon, and some other elements combined into solid particles, is so small that it would seem that, at least as a building material for stars, they can be disregarded. However, in fact, their role is great. They cool the hot interstellar gas, turning it into that cold dense cloud, from which the stars then emerge. The fact is that the interstellar gas itself cannot cool down. To cool down properly, it needs a cooler, the role of which is performed by interstellar dust particles. Unlike heavier and slower dust particles, gas molecules fly fast. During high-speed collisions with dust particles, they lose speed and their kinetic energy is transferred to the dust particle. In the same way, it heats up and gives this excess heat to the surrounding space, including in the form of infrared radiation, while it cools down. Thus, taking on the heat of interstellar molecules, the dust acts as a kind of radiator, cooling the gas cloud. Its mass is relatively small, about 1% of the mass of the cloud's matter. But this is enough to remove the excess heat over millions of years. When the temperature of the cloud drops, so does the pressure. The cloud condenses and stars can be born from it. The remnants of the material from which the star was born are, in turn, the source material for the formation of the planets. Such material contains large amounts of dust particles. The reason is that, when a star is born, it heats up and disperses the surrounding gas, while the dust is left to fly around. After all, it is capable of cooling and is attracted to the new star much harder than individual gas molecules. Eventually, a dust cloud ends up next to the newborn star, with dust-saturated gas at its periphery. The Earth was largely made of interstellar dust particles. The metallic dust particles became part of the planet's core, which is why the Earth now has a huge iron core. If a galaxy is formed, then the source of the dust is basically clear. Its most significant sources are novae and supernovae, which lose some of their mass by dropping the shell into the surrounding space. In addition, dust is also born in the expanding atmosphere of red giants, from where it is literally swept away by the pressure of radiation. There are quite a few relatively complex molecules in their cool, by the standards of stars, atmosphere, about 2.5 to 3000 Kelvin. But here's a mystery that hasn't been solved until now. It has always been believed that dust is a product of the evolution of stars. In other words, stars must have been born, existed for some time, aged, and, say, produced dust in the last supernova explosion. Only what came first? The egg or the chicken? Was it the first dust, which was required for the birth of a star, or the first star, which for some reason was born without the help of dust, got old, exploded, forming the very first dust? If the Big Bang theory is to be believed, 14 billion years ago, when the Big Bang occurred, the universe had no other elements but hydrogen and helium. It was then that the first galaxies, huge clouds, began to emerge from them, and the first stars formed in them, which had a long way to go. Thermonuclear reactions in the cores of stars had to cook the more complex chemical elements, turning hydrogen and helium into carbon, nitrogen, oxygen, and so on. After that, the star had to throw it all into space by exploding or gradually dropping its shell. Then this mass had to cool down and finally turn into dust. Yet 2 billion years after the Big Bang, in the earliest galaxies, there was dust. Using telescopes, it was found in galaxies 12 billion light-years away from us. At the same time, 2 billion years is a too short period for the full life cycle of a star. At this time, most stars don't have time to grow old. It is a great mystery how the young galaxy got dust if there should be nothing but hydrogen and helium. It is highly probable that small interstellar dust particles, preserving in their shells a few organic molecules, including the simplest amino acids, brought to Earth the first seeds of life about 4 billion years ago. Obviously, it is nothing more than a beautiful hypothesis, though it is supported by the fact that the amino acid, glycine, was found in the composition of cold gas dust clouds. Maybe there are others, but so far the capabilities of telescopes are not enough to detect them. We usually associate magnetic fields with stars and planets, but galaxies also have them. Magnetic fields play a major role in cosmic phenomena. In their time, they have worked hard to form the Sun and its surroundings, maintain the stability of galactic structures, influence cosmic rays, and control stunning processes in neutron stars and their surroundings. Cosmic magnetism rules at all levels of the organization of our universe. So how does magnetism arise, and where did it come from? In 1949, American astronomers William Hiltner and John Hall discovered the weak polarization of starlight in the Milky Way. In searching for an explanation for this phenomenon, they linked the polarization to the effect of the magnetic field on dust particles. A year later, scientists Leverett Davis and Jesse Greenstein estimated the magnitude of this field. Later, they found the same effect in the Andromeda Galaxy. This was the beginning of the study of cosmic magnetism. The origin of galactic magnetic fields is explained by two opposing concepts. Enrico Fermi put forward the hypothesis of relic magnetism, which arose shortly after the Big Bang. By the way, in 2006, Japanese astronomers supported this concept after conducting a series of studies. According to Fermi, galaxies captured and amplified these magnetic flows, resulting in the fields we observe today. Astrophysicist Eugene Parker explained galactic magnetism by the circular motion of the plasma in galaxies and their clusters. Later, this model of galactic dynamo was developed by other scientists. Although the theories of relic fields sometimes look very elegant, and some may even be correct, it is still necessary to accurately measure intergalactic magnetism, and this hasn't yet been accomplished. The fields inside galaxies and galactic clusters are another matter. Their occurrence is well described by the theory proposed 60 years ago by the German astrophysicist Ludwig Biermann. This mechanism is called the Biermann battery. Magnetic fields can also arise in other ways, for instance, in the rotation of plasma falling on a black hole. Nature has many ways to enhance this magnetization, for example, by compressing the cosmic plasma with shock waves. Such processes constantly occur in spiral galaxies, which ensures the stability of their internal magnetism. Galactic magnetic fields are also associated with the processes of star formation. It has long been known that stars arise as a result of the gravitational condensation of cold and relatively dense clouds of cosmic gas. Such clouds, each inch-3 of which contains from tens to millions of particles, sometimes extend for hundreds of light years. Particularly dense and vast clouds can give rise to hundreds or even thousands of stars. The processes of their birth appear to be completed rather quickly, within 10 to 15 million years at most. But the details of this process are not yet clear. Ordinary, baryonic, matter of outer space is a fully or partially ionized gas, which is a good conductor and therefore reliably holds magnetic fluxes so that in the interstellar environment the magnetic field lines almost never disappear completely. Such indicators are also typical for other spiral galaxies. In galaxies particularly rich in gas and, as a consequence, young stars, the magnetic field magnitude is larger, and in their central zones even larger. Elliptical galaxies are poor in gas, and therefore their magnetic fields are much weaker. However, as already mentioned, it is very difficult to measure the fields, so information about their magnetism is very fragmentary. Fields with induction also penetrate galaxy clusters, but magnetic fields haven't yet been found in the cosmic space separating such clusters. If they do exist, then they are extremely weak and most likely preserved from the infancy of our universe. Nowadays, almost all astrophysicists agree that a typical star emerges in 4 stages. First, the gas, or gas dust, cloud gets fragmented and clots of high-density matter are formed in it. Then, each of the clots is compressed by gravitational force, with gravitational collapse starting in the center of the clot and spreading to the periphery. This is how spherical protostars surrounded by rotating flat disks are formed. But the protostar won't become a luminary until it borrows a fair fraction of its matter from the disk. If this happens, this is the 3rd stage, the protostar rapidly acquires additional mass, shrinks even more, and greatly heats up its own core. Eventually, its temperature reaches a few million degrees and the thermonuclear combustion of hydrogen begins. The protostar transforms into a star. In fact, galactic magnetic fields might play an important role in these processes. For the matter of the disk to fall on the protostar, it must lose some of its rotational momenta. This is precisely what the magnetic field contributes to. Already at the stage of disk formation, it bends the paths of protons, which collide with neutral molecules and also change their trajectories. This magnetic braking leads to internal friction, which reduces the rotational momentum. Later, when the disk is shaped, the rotation slows down due to another physical mechanism, magnetorotational instability, which links the inner and outer belts of the disk and makes the former rotate slower and the latter faster. The life of main sequence stars ends with their transformation into compact objects, such as white dwarfs, neutron stars, or black holes. The latter has no magnetic field of their own, possessing only mass, angular momentum, and electric charge, while the others have magnetic fields that can reach fantastic values. A white dwarf forms after the gravitational collapse of a star that has exhausted its fuel reserves. For the vast majority of white dwarfs in the Milky Way, it is impossible to measure the magnetic field. But those that can be measured are highly magnetized, far more so than the Sun. They owe this to the collapse of an already magnetized parent star, which tightly compresses its magnetic field lines and thus increases the magnetic field by thousands of times. But the absolute record breakers for the magnetic part are neutron stars. Usually, their magnetic field value near the surface is 10 to the power of 12 Gauss. But sometimes the magnetic field magnitude is hundreds or thousands of times greater than this value. These stars are called magnetars. The magnetic fields of ordinary neutron stars, like those of white dwarfs, arise during the collapse of the parent star, but with immeasurably greater compression. The magnetic flux of such a star is closed inside a sphere with a radius of about 6 miles, instead of several thousand miles for a white dwarf, and the field in such compression is much stronger. But if you are seriously interested in astrophysics, then you probably have a question. Where does magnetism come from if neutrons have no electric charge? They have a magnetic moment, but it gives a completely negligible contribution to the magnetic field. The fact is that such stars are composed not only of neutrons. Their surface layers most likely consist of ordinary matter, and in the depths, there are charged particles, protons and electrons. They can participate in convective processes, generating currents in the interior of the star, which become the source of such a strong magnetic field. In the depths of a neutron star, originating from a strongly magnetized main sequence star and rotating at over 1,000 revolutions per second, a powerful dynamo is activated in the first moments of life, which accelerates the magnetic field magnitude to gigantic values. Together with the term magnetar, which was coined not so long ago, there is a theory according to which, in just a few seconds, the core of such a neutron star cools down so much that convection stops and the dynamo stops working. However, the super-strong magnetic field persists for a long time, because it is frozen in a superfluid environment, which has extremely high electrical conductivity. It is even possible that it is a superconductor. The magnetic field takes some of the kinetic energy from the star and gives it away in the form of radiation and particle emissions. Therefore, the rotation period of the magnetar grows rapidly, reaching a few seconds in just 10,000 years. This is exactly the angular velocity of almost all currently known magnetars. The magnetic power of neutron stars turns them into sources of continuous directed radio emission. The method of its generation is not yet known in detail, but the general explanation is as follows. The rotating magnetic field of a neutron star induces extremely strong electric fields, bouncing charged particles off its surface. These particles begin to move in spirals with a very dense winding, directed along the magnetic field lines. Such motion generates narrow beams of radio waves that escape into space along the magnetic axis of the neutron star. Since this axis doesn't coincide with the axis of rotation, each beam of radio waves outlines a conical surface in space. When the Earth crosses such a surface, the radio telescope receives radio pulses that follow each other at equal short intervals. Such sources are called radio pulsars. There are also more rare varieties of space illuminators, optical, X-ray, and gamma-ray pulsars. Magnetars work differently. These exotic stars irradiate the cosmos several times at a time in short but extremely powerful bursts of soft gamma rays and X-rays. The magnetar fields are so strong that they are unable to remain stable for long. Little by little they deform and cause strong stresses in the substance of the shell, localized in small areas. When the stress exceeds the strength limit of the crust, it bursts and breaks very rapidly, in about 1/10 of a second. The magnetic field in this place breaks out and spirals, creating the strongest perturbations of the magnetosphere. As a result, concentrated beams of high-energy photons that we register as bursts of soft gamma rays and X-rays are generated. As a rule, the first giant burst is followed by weaker ones, and the magnetar gradually shuts down. However, this exotic object deserves a separate video, since it is too mysterious and powerful. Why is the universe 13.7 billion years old? Why is our solar system 4.5 billion years old? And not, say, 6 billion or 600 million years old? How is the age of the universe, as well as the Earth, the solar system, and the Milky Way galaxy known? I'm sure many people have wondered about this question, which, by the way, has been of interest since ancient times. In fact, this question is one that only modern science has been able to answer. Until the second half of the 18th century, it was believed that the universe was eternal and unchanging. Later, it was thought that the creation of the world occurred in 3929 BC, based on an analysis of biblical texts. It wasn't until 1787 that French naturalist Georges Louis Leclerc concluded that if our planet had been a ball of molten iron at birth, it would take 75,000 to 168,000 years to cool down to its present temperature. In other words, he estimated the age of the Earth and the Sun based on physical models. 108 years later, Irish mathematician and engineer John Perry recalculated the thermal history of the Earth and determined its age at 2 to 3 billion years. At the very beginning of the 20th century, Lord Kelvin came to the conclusion that if the Sun gradually shrinks and shines solely by releasing gravitational energy, the age of our star, and, therefore, the maximum age of the Earth and other planets, could be several hundred million years. But at that time, geologists could neither confirm nor refute these estimates due to the lack of reliable methods of geochronology. In the middle of the first decade of the 20th century, Ernest Rutherford and American chemist Bertram Boltwood developed a framework for radiometric dating of terrestrial rocks, which showed that Perry was much closer to the truth. In the 1920s, mineral samples whose radiometric age approached 2 billion years were found. Later geologists have repeatedly raised this value, and by now it has more than doubled to 4.4 billion years. More data is provided by the study of celestial rocks, meteorites. Almost all radiometric estimates of their age fall within the interval of 4 to 4.6 billion years. Modern helioseismology makes it possible to directly determine the age of the Sun, which, according to the latest data, is 4.56 to 4.58 billion years. Since the duration of the gravitational condensation of the protosolar cloud was counted only in millions of years, we can confidently state that no more than 4.6 billion years have passed from the beginning of this process to our days. Solar matter contains many elements heavier than helium, which were formed in the thermonuclear furnaces of massive stars of previous generations, which burned out and exploded in supernovae. This means that the extent of the existence of the universe greatly exceeds the age of the solar system. In order to determine the measure of this success, it is necessary to go first to our galaxy and then beyond its limits. The lifetime of our galaxy can be determined in different ways, but we will limit ourselves to the two most reliable. The first method is based on monitoring the glow of white dwarfs. These compact and initially very hot celestial bodies represent the final stage in the life of almost all but the most massive stars. To become a white dwarf, a star must completely burn off all of its thermonuclear fuel and undergo several cataclysmic events, such as becoming a red giant for a while. A typical white dwarf is composed almost entirely of carbon and oxygen ions immersed in the degenerate electron gas and has a thin atmosphere dominated by hydrogen or helium. Its surface temperature ranges from 8,000 to 40,000 K, while the central zone is heated to millions or even tens of millions of degrees. According to theoretical models, there may be dwarfs composed mainly of oxygen, neon, and magnesium, which, under certain conditions, turn into stars with masses of 8 to 10.5 or even up to 12 solar masses. Still, their existence has not yet been proven. The theory also states that stars with at least twice the mass of the Sun end up as helium white dwarfs. Such stars are very numerous, but they burn hydrogen very slowly and therefore live many tens or hundreds of millions of years. Since a white dwarf cannot sustain fusion reactions, it shines due to stored energy and therefore cools down slowly. The rate of this cooling can be calculated and, on this basis, we can determine the time needed to decrease the surface temperature from the initial one. For a typical dwarf this is about 150,000 K, to the observed one. Since we are interested in the age of the galaxy, we should look for the longest lived, therefore also the coldest white dwarfs. Modern telescopes allow us to detect intragalactic dwarfs with a surface temperature of less than 4,000 K, whose luminosity is 30,000 times lower than that of the Sun. So far they haven't been found. Perhaps they don't exist at all, or there are very few of them. It follows that our galaxy can't be older than 15 billion years, otherwise they would be present in appreciable quantities. This is the upper limit of age. And what can be said about the lower one? The coldest currently known white dwarfs were recorded by the Hubble Space Telescope in 2002 and 2007. Calculations have shown that their age is 11.5 to 12 billion years. We must also add to this the age of the progenitor stars, from half a billion to a billion years. It follows that the Milky Way is by no means younger than 13 billion years. So the final estimate of its age, based on observations of white dwarfs, is about 13 to 15 billion years old. That is the first method. The second one is based on the study of globular star clusters located in the peripheral zone of the Milky Way and orbiting its nucleus. They contain from hundreds of thousands to more than a million stars, connected by mutual gravity. Globular clusters exist in almost all large galaxies, and their number sometimes reaches many thousands. New stars are practically never born there, but elderly luminaries are present in abundance. About 160 such globular clusters have been registered in our galaxy, and perhaps 2 or 3 dozen more will be discovered. The dating of the formation of the oldest globular clusters allows us to set the lower limit of the galactic age as well. It is very complicated technically, but it is based on a very simple idea. All cluster stars, from the supermassive to the lightest ones, are formed from the same gas cloud and are therefore born almost simultaneously. Over time, they burn out the main hydrogen reserves, some earlier, others later. At this stage, the star leaves the main sequence and undergoes a series of transformations, which culminate either in a complete gravitational collapse, followed by the formation of a neutron star or a black hole, or in the formation of a white dwarf. Therefore, the study of the composition of a globular cluster makes it possible to determine its age quite accurately. For reliable statistics, the number of clusters studied should be at least several dozen. Monitoring of 41 globular clusters in our galaxy showed that their average age is 12.8 billion years. However, our galaxy must be older than its clusters. Its first supermassive stars exploded supernovae and ejected into space the nuclei of many elements, in particular, the nuclei of the stable isotope beryllium, beryllium-9. When globular clusters began to form, their newborn stars already contained beryllium, and the more of it the later they arose. By the beryllium content in their atmospheres, we can figure out how much younger the clusters are than the galaxy. As the data for the NGC 6937 cluster show, this difference is 200 to 300 million years old. Therefore, we can say that the age of the Milky Way exceeds 13 billion years and possibly reaches 13.3 to 13.4 billion years. This is almost the same estimate as that based on observations of white dwarfs, but it is obtained in a completely different way. But how was the age of the universe estimated? The scientific formulation of this question became possible only at the beginning of the second quarter of the last century. In the late 1920s, Edwin Hubble was engaged in refining the distances to dozens of nebulae outside the Milky Way, which only a few years earlier had come to be considered independent galaxies. These galaxies are moving away from the Sun at radial velocities, which have been measured by the redshift of their spectra. Although the distances to most of these galaxies could be determined with a large error, Hubble still found that they were roughly proportional to the radial velocities. 2 years later, he confirmed this conclusion based on observations of other galaxies. Some of them are more than 100 million light-years away. This data formed the basis of the famous formula, known as Hubble's law. Here v is the radial velocity of the galaxy in relation to the Earth, d is the distance, and h0 is the constant of proportionality. In 1927 Georges Lemaitre showed that the general theory of relativity allows us to interpret the movement of galaxies as evidence of the expansion of the universe. 4 years later he had the courage to take this deduction to its logical conclusion by hypothesizing that the universe arose from a virtually point-like embryo, which he, for lack of a better term, called an atom. This primordial atom could stay in a stable state for any time up to infinity. But its explosion gave birth to an expanding space filled with matter and radiation, which in a finite time gave rise to the present universe. Based on this work of Lemaitre and the later works of Hubble and other cosmologists, it was explicitly stated that the age of the universe, of course, counted from the initial moment of its expansion, depends on the value, which is now called Hubble time. The nature of this dependence is determined by a particular model of the universe. If we believe that we live in a flat universe filled with gravitational matter and radiation, then to calculate its age, Hubble time must be multiplied by 2/3. That's where the hitch occurred. From Hubble's measurements, it emerged that the universe was born 1.2 billion years ago, which clearly contradicted even the severely underestimated assessments of the age of the Earth at that time. It was possible to get out of this quandary by assuming that the galaxies were moving apart more slowly than Hubble had thought. Over time, this assumption was confirmed, but it didn't solve the problem. In general terms, this contradiction was resolved in 1998 to 1999, when two teams of astronomers proved that over the past 5 to 6 billion years, outer space has been expanding at an increasing rather than decreasing rate. This acceleration is usually explained by the fact that in our universe the influence of the anti-gravity factor, the so-called dark energy, the density of which doesn't change with time, is increasing. The duration of the existence of the universe with an anti-gravity component doesn't have to equate to 2/3 of Hubble time. Therefore, the discovery of the accelerating expansion of the universe, awarded the Nobel Prize in 2011, made it possible to eliminate the divergence between the cosmological and astronomical estimates of its lifetime. It was also a prelude to the development of a new method for dating its birth. On June 30, 2001, NASA sent the Explorer 80 probe into space. It was able to register the temperature fluctuations of microwave cosmic rays with an angular resolution of fewer than 0.3 of a degree. Fluctuations of relic radiation are generated by density variations of the electron-photon gas, which once filled the cosmic space. When this temperature fluctuation dropped to nearly zero, almost all the free electrons fused with the nuclei of hydrogen, helium, and lithium, thus giving rise to neutral atoms. Before that, sound waves were propagating in the electron-photon gas, which was influenced by the gravitational fields of dark matter particles. These waves imprinted on the spectrum of relic radiation, which can be deciphered using the theoretical apparatus of cosmology and magnetic hydrodynamics. As the latest calculations show, its most probable extent is 13.799 billion years. Thus, astronomers, estimating the age of the universe in 3 different ways, got quite compatible results. So now we know, or, to put it more cautiously, we think we know, when our universe emerged, at least within a few hundred million years. Who knows, perhaps someday our descendants will add the solution to this age-old riddle to the list of the most remarkable achievements of astronomy and astrophysics. If you were interested, then give thanks to our channel. You can do it by giving a like to this video and writing a comment.